We want to welcome you to the Dallas Independent School District STEM Environmental Education Center virtual field trip. We want to say a very special welcome to Nancy Cochran, LP Coward, Edward Tatch, Harold Budd, Withers, Rosa Parks from Lancaster ISD, Go Tigers, and Purefoy from Frisco ISD. Thank you so much for joining us today. Teachers, if you're watching and you have not signed up, please do so. Go to www.tiny.cc/3-5 registration. Fill out a real short little form and we'd appreciate it. The program today will be force in motion. During this virtual field trip, students will observe how position and motion change by pushing and pulling objects. Students will also observe magnetism and gravity acting on objects. Ms. Ramirez will do how objects swing. Mr. Dominguez will talk about push and pull. Ms. Ram will cover magnetism. Mr. Monroe will do gravity. During this virtual field trip, you cannot ask us questions, verbal questions, but you can ask us questions by going to www.tiny.cc/question-answer and fill out a short form and send it in. And I will be glad to try to answer them during the program. If not, I'll send the answers back to your questions. And now I'm going to stop sharing my screen. And Mr. Ramirez is going to tell you how objects swing.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning how position and motion can be changed by swinging things. So before we get started, I actually have an animal friend, and this animal friend actually likes to play with things that swing. So I'm going to give you some clues to who you think this animal is, and then I'll let you guys make your guess. So this is one of the favorite toys of this animal. So notice it has lots of swinging things for this animal to chew on and play with. This animal also has really tall, long ears. This animal can run and jump rather fast. This animal is a mammal because it is covered with fur. So go ahead and make your guess to who you think this animal is, and I'll go ahead and pull him out. And if you guys said a rabbit, you would be correct. So this is Pfeiffer. He's one of my newest rabbits. So Pfeiffer here is a mammal because he is covered in fur and he loves to play with a variety of different toys. And his favorite ones are probably the toys that swing. And we're going to be learning about swinging things today. So I'm going to go ahead and put Pfeiffer up. And I have a quick little video to show you. It's an example of one of my other rabbits playing with some swinging objects. So let me share my screen with you guys and I'll show you guys that video super quick. And we're going to be looking at some of the forces involved with swinging things. Now, we can refer to those swinging things as a type of pendulum. So we're going to describe the motion of the pendulum. So here I have, it's just a string hanging from the top of the cage, and at the very bottom is a little bell. And you'll notice that it's swinging back and forth. So the rabbit, that happens to be Baby Bunny Lucky, when he pushes on the bell with his nose, it starts that swinging motion. And it continues to swing because gravity is trying to pull that bell back down. And eventually, if he stops playing with it, that bell will stop swinging because friction will slow it down. And friction is simply a force that slows down any motion. So I'm going to go ahead and stop that screen share and we'll take a closer look at some of those words that I just went over. So again, I said we're going to be learning about swinging objects. So one of those objects that I have is a pendulum. So let's talk about the history behind a pendulum. So the story goes that in about the 1500s, a now famous scientist named Galileo was sitting in a church in France. And he happened to look up and he noticed that the chandelier, so this is a chandelier, he noticed that the chandeliers were swinging back and forth. Now, sometimes they were doing like really big swings and sometimes they were just doing little swings. But being a good scientist that he was, he asked, well, why is that? So he decided to create an experiment to test why that pendulum, that swinging object, was moving the way it was. And we consider Galileo the father of experimental science because he designed a lot of experiments. And we're going to design our own experiment with a pendulum. So let me show you guys my pendulum that I made. So here's my pendulum. And again, a pendulum is just, think of anything that swings. So think of some pendulums that you guys might see at home or at school, maybe on a playground. So those would be pendulums. And there are a couple of components to our pendulum. We have a support bar. So right here's my bar. We also have, it's called the arm. In this case, my arm is going to be the string. So the arm is attached to the support bar. And attached to that arm, we have what's called the bob. It's just the weight. So in this case, the way our pendulum works, if I take my bob or my weight, if I pull it up and then I drop it, the force of gravity is what is pulling that bob back down. And because I started that motion by applying a force, this bob is going to keep moving back and forth because of a special force called inertia. Inertia simply says that objects in motion will stay in motion unless acted upon by another force. So let's go ahead. I pulled it, so I'm applying a pulling force. I'm going to drop it. Gravity is pulling it down. It's going to keep moving because of inertia. And inertia says that it will stop moving if another force acts on it. What do you think that other force is that's acting on it that is trying to slow it down? Even though you can't see it, there's actually air resistance in this room, and that is what is slowing down the pendulum. So there's a couple of forces working with our pendulum. We have gravity, which is pulling the bob down. We have inertia, which is what keeps it moving until our friction comes into play. And friction is what is slowing down the pendulum, eventually causing it to stop. So we're going to do a little experiment, and we're going to see what string length will actually have the most number of swings in 15 seconds. So we're going to do a little experiment. So again, our question is, how does the length of string affect the number of times a pendulum will swing? And I know this is 30 seconds, but for time purposes, we're going to cut it down to 15. And we're going to record our data in a little table just like this. So go ahead and make your guess which string will swing the most number of times in 15 seconds. The short string, the mid-sized string, or the super long string. So make your guess and maybe think about why did you make that guess. And I'm going to start my timer. We're going to start with the short one first. And I know it's going to be kind of hard for you guys to see, so I'm going to hold my hand behind it and I'm going to count out loud. So every time the pendulum swings forward and then comes right back, when it comes back to my hand, we're going to count that as one full swing. So for example, if it starts here, it goes forward and back, that is one full swing. So let me start our 15 seconds and then we'll get started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, oops, and it stopped. So that was about 30. So let me go ahead and stop our timer and put down 30 for the short one. And my timer still wants to keep going. There it goes. And now let's do our 10 centimeter one. So this one swung 30 times back and forth. How many times do you think the 10 centimeter string is going to swing? So I'm going to apply my force. I'm going to pull it up and gravity is going to do its thing and start to pull it down. So let me start it and then we'll do our count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 20. Oops. We'll do that at 24. So hopefully you guys notice a little bit difference in the speed on how fast these were going. So the middle one went only 24 swings. Make a guess. How many times do you think the super long pendulum will swing? So again, I'm going to apply my force. I'm going to pull it up. Again, gravity will do its thing and start the motion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, oops, 13, 14, 15, 16, 17, oops. So that was 17, and it did have a little accident, it hit that, but that shouldn't make too much of a difference. So here's our results. So let me move this out of the way. Now for our first test, we had 30 swings for the short one, 24 for the middle one, and 17 for the super long string. Now, a good scientist would repeat this at least 2 more times, but for time constraints, we're just going to do it 1 time. But we can already see a pattern. So our results tell us that the shorter the string, the more times it is able to swing in the 15 seconds. So that's our results. And something that you guys can do at home, you can actually create your own pendulum, and you can finish off this experiment at home. All you need is, I used a pencil, a piece of string, and a paper clip, and you can do the same experiment. You can try and test different variables. What happens if you use something light versus something heavy at the end? What happens if you start way up high versus starting way down low? And again, you can experiment with trying different lengths of string. So this is a super easy pendulum that you guys can make at home or school. And then you can also go on a pendulum hunt. So maybe look around your school or at home and see what are some examples of pendulums or swinging objects that you guys can find, and think about those forces that are involved with that motion. So that is all I have for you guys for pendulums. We're going to give it back to Dr. Gorman to answer any questions.
Thank you, Ms. Ramirez. And a student did ask, what force causes a pendulum to swing? The force that causes the pendulum to swing is gravity. When you displace the pendulum from its resting position and release it, gravity makes it swing back and forth. Thank you again, Ms. Ramirez. Now, Mr. Dominguez is going to tell you about push and pull.
Hey guys, it's Mr. Dominguez, and what you're watching is the entire EEC staff take a little trip down to the Post Oak Preserve to do some water quality testing at our lake. But this video is not about water quality, it's about force and motion. I was thinking as we drove, accelerated, decelerated, and changed directions, that the motion of driving is a really good example of what unbalanced forces do to a balanced system. You may be wondering 2 things right now. What's an unbalanced force? And maybe even what a force is. Well, in this portion of your virtual field trip, I will talk to you about force in regards to motion. I will define a push and a pull, and I will also talk about how unbalanced forces change a balanced system. So guys, let's get moving and let's get this presentation started. Alright guys, let's talk about motion first. And what is motion? So simply put, motion is the movement of an object from place to place. So let me demonstrate. If I move this isopod plushie from the center to this location, was it in motion? I think it was. If I move it back to its initial location, was it in motion? Yes. So as I move the plushie from place to place, it is in motion, okay? So that's what motion is. However, in order for motion to occur, there needs to be forces applied to the object for that movement to happen. So what are 2 forces that we can apply to this isopod? Well, what did you see? If I move it this way, like I did at the beginning, what did my hand do? It pulled it to the right. Now, if I were to move it over here, what is my hand doing? Let's repeat that. What am I doing? I'm pushing it, right? So the forces that make movement possible are a push and a pull. So let's review what we just learned. So we learned that motion is an object's movement from place to place to place to place, and that in order for that movement to occur, there needs to be forces applied to that object in the form of either a push or a pull. Hey guys, so I'm about to set up a demonstration that will show us how unbalanced forces work. But before I do that, I want to set up a balanced system, and I'll be doing that with a lemon. Some people use eggs. Just in case our demonstration goes wrong, I prefer to use lemons, less of a mess. We're going to need a plate. I have this aluminum plate, baking plate right here, but any plate will work. You're going to need a used toilet paper roll or napkin roll, doesn't matter, and a glass of water. So what we're going to do is we are going to set up a system in which our forces are balanced, okay? So what we're going to do is we're going to take our glass of water. We are going to put the plate on top of the glass of water and our roll of toilet paper in the middle, and followed by our lemon. So as you can see, after I set this up, there's no movement. So all the forces that are acting on this lemon are balanced. And what forces are we talking about? Well, we're talking about our gravitational force and the reactive force that acts equally but in the opposite direction. So what we're going to do in order for any movement to occur in this system is introduce an unbalanced force, but we'll do that in slow motion so you guys can get a better look at what that unbalanced force was. And please let me know if it was a push or a pull. So let's take a look. So guys, consider the way that you move, and let's examine how these adorable animals are moving themselves. They are constantly exerting a series of pushes and pulls that are unbalanced forces that allow them to overcome the gravitational forces and the friction and the air resistance, all of those forces that want to keep them stationary. In order for us to move and do things like hop, jump, and for these animals hunt, unbalanced forces are the key to movement. Alright guys, I hope you enjoyed this portion of your virtual field trip. Here we have Ollie demonstrating the forces needed for a comfy nap. You can see him pushing and pulling his way into a comfortable position. Alright guys, until next time, have a great day.
Thank you, Mr. Dominguez. Next student wants us to give another example of push and pull. So an example of push as a force would be to push on a swing. The force moves the swing in a particular direction, and the harder that you push, the further the swing will go. The example of a pull as a force would be opening a door. If you pull on it lightly, the door won't hardly open, but if you pull with greater strength, the door opens enough. If you pull the door very hard, it will slam into the wall behind you or beside you or whatever. And now we're going to have Miss Ram tell us about magnetism.
Good afternoon, everybody. I'm Miss Ram,
And like Dr. Gorman said, we are talking all about magnetism. So at the end of my part of the presentation, you'll be able to observe magnetic forces acting on objects. So there are a couple questions I want to explore while we experiment with our magnets today. So how do magnets interact with other objects, and how do they interact with one another? And here are some pictures of different magnets you might have in your classroom that I also use here in the science lab. So before we experiment with our magnets, let's talk about the bar magnets. So we are going to use these little bar magnets first, and you'll notice that there is a red side and a blue side, and on your screen there is a little N and S. Those stand for the North Pole and the South Pole of a magnet. So every single magnet has a North and South pole, but these are kind of color coded so that when we use them in the classroom, we know which side is which, and we can easily tell. So first, we're going to see how these magnets interact with each other. So if I bring a North Pole to another North Pole, what's going to happen? If I put a North Pole and a South Pole together, what's going to happen? And then two South Poles together. So let me stop sharing, and then we are going to try. So I'm going to put my magnet here. I've got the North Pole facing in, and I'm going to bring another magnet in with its North Pole facing. Whoop. And what happens? It pushes it away. It's pushed it so much that it turned it around. So if you were holding these in your hands, you would be able to feel that magnetic force repelling. They are pushing apart. So it's really hard for me to get them close. They're pushing apart so hard, they do not want to touch. So if I leave this magnet here and I bring in the South Pole, I'm going to approach the magnet, and whoop, once I get close enough, the South Pole pulls the North Pole in. So once again, if you're holding these, you can feel the magnets attract. They pull together. All right. So using what we just learned from the other two experiments, let's see, what do you think is going to happen when I bring this South Pole closer to this one? So I'm going to bring it in. Whoop. It pushes it away, and it even pushes it so much it flips it around. So once again, I can feel that magnetic force repelling. All right, so let's look at our little results and see what conclusions we can draw from that. Oop. Okay, so we brought the North Poles together. The magnets repelled, they pushed apart. When we brought the North and South Pole together, they were attracted, they pulled close. Then when we brought the South Pole and the South Pole together, it repelled again. They did not want to be near. So that can help us draw the conclusion that alike poles or similar poles repel, they push apart, and opposite poles attract, so they pull closer. All right, so we're going to use some of that in our experiments coming up. But first, I want to talk about the magnetic field. So here is a little bar magnet like the ones we were just using. And someone took some of the metal iron and kind of shaved off tiny little pieces. So it's like almost like a little powder or like glitter. So they sprinkled it around so we could see what the magnetic field would look like if we could see it with our eyes. So I told you, you can feel the magnetic force, but you can't see it. So that's just a way that we can see the pattern of the magnetic field. All right, and then on the right is just a little diagram with those lines being a little more clear so we can see what it would look like if we could see it. So the magnetic field is just the area that's affected by a magnet. So the larger the magnet, the larger the magnetic field. So larger, more powerful magnets would be quite large, right? All right, so we are going to experiment with a few different things. So let me take you back to my table. And first, I want to hold up a paper clip. Now, if I can hold it still so it's not swinging so much, I can show you that when I bring my magnet near, it can change the motion because the magnet is the magnet attracts the paper clip. So Magnets are attracted to metal objects that contain iron, nickel, and cobalt. So this paper clip must have one of those metals inside. So I can move the paper clip, stop the paper clip with my magnet. All right, let's see, what else do I have? So I have a compass. You may have used these at school before. If you're hiking or you're out in the woods somewhere where you don't have GPS, this can help you know which direction you are traveling in. So remember I said the larger the magnet, the larger the magnetic field. Well, the Earth is one giant magnet. You may already know we have a North Pole and a South Pole, but we also have a North magnetic pole and a Southern magnetic pole. So the way a compass works is the little arrow is attracted to the North Pole. So it's always pointing north. Now this one's a little funky and it's not calibrated correctly. So don't pay attention to what letters or numbers it's pointing towards because it's been in my magnet box. So it's a little wonky. But you can see that when I bring my magnet near, it changes the motion of that arrow. So I can actually use my magnet to manipulate which way the arrow is pointing. So if I flip my magnet around, then the arrow flips around. Like I said, this one's a little wonky because it's been sitting with a bunch of different magnets in the box for a while. So it might have to get like recalibrated. But either way, you can see that it interacts with the magnet. So this, if it was working correctly, and there wasn't any magnets close by it, you just had this on the trail, the red arrow would be pointing north. Okay, so let's see, what else do I have for you? Two more things. I have a little toy car and I want to push and pull the little toy car with my magnet without touching it. So I'm going to scooch it down to my table so you can see. And remember what we learned about similar poles and opposite poles. If I want to, here, let's see. I want her to travel forwards this way. So this is the front of the car, the North Pole. So if I want to push her forwards, I need to put my South Pole to the South Pole. And it'll kind of bump her and make her move. It's kind of making her turn. But either way, it pushes her forward. It pushes her away from this end of the magnet. Boop, boop. But they really want to attract. So if I put my South Pole to the front of the car to the north, it will pull it closer. So I'm actually able to move her that way too. Otherwise, when I push it, she really wants to just turn around. But either way, it works. So I can make her car move without touching. All right. Then I wanted to show you those iron filings. So I showed you that picture that had iron filings sprinkled around the bar magnet. I'm not going to do that because it's going to make a big mess. But I wanted to show you what happens when I bring my magnet near. So let me see, make sure you're in focus. If I bring my magnet near, you can see the iron filings start to move. I'm actually able to drag them up the side of the glass and move them around within my beaker. So if I take little round magnets, just like you might have on your fridge or on your whiteboard in your classroom, just like this, I can drag some of the iron filings to the side of the beaker and keep them there. So it just stands up by itself. Then, let's see, my magnet. See, if I hold it just here without the iron filings, what happens? Boop, it falls. But if I have the iron filings, it is attracted to it and it stays up. Oh, also WC wants to introduce himself. Thank you, WC, for the interruption. You are cute, but get out of here. Thank you. All right, and so these would stay there the whole time. You can also see it a little more clearly without the reflection of the glass. If I take the same iron filings in a Petri dish and bring my magnet near, underneath, I can also drag those iron filings around. It's like that little Woolly Willy toy where it has a man's face and you drag the little iron filings around and make him a funny mustache or eyebrows. So there we have it. Iron is attracted to the magnet.
All right, now we're gonna look at some other examples of magnetism in real life. Boop. So like I said, the compass has magnets inside. There's a picture of a maglev train. That's a train that levitates on the tracks because there are magnets underneath and there are magnets on the tracks itself, and they change polarity so it's propelled on the tracks. It's really cool. Then computers, speakers, all different kinds of technology use magnets inside. Your iPhones, your iPads, the screen you're watching this on now, all those things use magnets. Also electric motors, MRI machines when you go to the doctor, and even in your kitchen, refrigerators, microwaves, all those appliances use magnets to work. All right, so just to review our magnetism vocabulary, the opposite poles, they attract, they pull together. When the similar poles are together, they repel, they push apart. And magnets attract metal objects, including iron, nickel, and cobalt. So my challenge to you before I send you off is later this afternoon, maybe in your classroom or at home, try to explore and see more examples of magnetic and non-magnetic objects. All right, I hope you had fun, and I'll see you next time.
Thank you, Ms. Ram. Question did come in. Does the compass, the red arrow on the compass, point towards true north, geographic north, or the magnetic north? Magnetic compass does not point to the geographic North Pole. A magnetic compass points to the Earth's magnetic poles, which are not the same as the Earth's geographic poles. Thank you again, Ms. Schramm. And now Mr. Monroe is going to tell us about gravity.
Good afternoon, students. My name is Mr. Monroe, and we're going to be looking at this tremendous force that we call gravity. And I'm going to go back and talk about I guess he was very outstanding, very smart guy, Sir Isaac Newton, who discovered gravity. And it's really funny, according to legend, he was out studying the forces of nature and he noticed an apple falling from a tree. Well, back when I was going to elementary school, according to the legend at that time, and I don't know what happened, but according to that legend that we were told, the apple actually hit him in the head. Now, we don't know whether that's true or not, but whatever happened, it allowed Newton to come to the point where he realized there had to be some force that must be acting on falling objects. Otherwise, they would not start moving from that state of rest. And so that's how gravity was discovered. Now, Mr. Dominguez did an excellent job talking about pushing and pulling and had, wow, an outstanding little experiment there that dealt with unbalanced forces. So to really show you the effects of gravity, I'm going to talk a little bit about unbalanced forces and balanced forces by simply looking at this great big book that I'm holding here, holding it right here. And I'm exerting force to hold this book up. Now, there's another force working on it, gravity. And so the force that I'm holding underneath the book is a balancing active force that's keeping the book from succumbing to gravity. If I take away the force of my hands holding this book up, look what happens. The book goes into what we call a free fall. And what that means is there's nothing except gravity working on that book. And the closer it gets to the source of gravity, which is the center of our planet, the velocity or the speed is going to accelerate of the object that is being pulled by gravity. Now, gravity is a force that pulls objects straight down, okay? One of the things that Sir Isaac Newton found out is that the more mass an object has, the greater its gravitational force. Just one more time, I want to show you, we have a little ball up here that's at rest. Now, if I release it, from there, gravity is falling on it and free fall. Now, you may not believe this, students, but you can take a large object and a small object and drop them from the same height, and they will accelerate or travel at the same speed. Here I have two objects right here. I have a leaf and I have an acorn, okay? Now, it's not going to happen in this room because Ms. Ramirez, she talked about friction and air resistance. If I could create a condition where these would be in an area where there would be no air resistance, believe it or not, these two items would have the same acceleration or the same speed being pulled down as each other. They would have the same speed. They will accelerate at the same rate. And if I drop them now, because I know that there's air circulating in here, so we've got a bit of friction and we've got air going on. Yeah. So the acorn did beat that time, okay? Listen, there are a lot of things that involve gravity on the surface of our planet. It affects us in a variety of different ways. Remember, gravity is holding us in place. And it also is a very active ingredient on how our world changes. For example, there are earth processes that happen in our world today simply because of the effects that gravity have on. Now, I've chose today to use water, and I've got a stream table here that I have set up to show an earth process that involves something that we call erosion. And erosion is the transporting of materials such as soil and rocks. And that usually happens on the surface, or in fact, it happens on the surface of our planet, and it can create different landforms that we get a chance to see in our everyday lives. Well, I've created this stream table, and so let's take a look at it. And I planted a couple of trees in here, you can see that. And of course, it's elevated. And that means it's high at one end and low at the other end. And what I'm going to do is use a little water, going on the pretense that at the higher elevations in this demonstration, there is a lot of rainfall that is causing a bit of flooding. So watch what happens, guys. We have created what appears to be a river. Now, at the bottom of that river, we have created another landform, and I don't know whether you all can see that, but I'll bring it up so you can see it. We have created what we call a delta. Now, I'm going to put this down, and I want to share this with you. Water and gravity, they create the strongest erosion agent on our planet. So gravity is a big factor in creating the different landforms that we see all over the surface of our planet, okay? Now, gravity is also used to do work. A few minutes ago, I had done this program, and I had found an instrument that my mother used many, many years ago. That instrument was a timer. You heard Ms. Ramirez, she was using a timer, but I bet it wasn't anything like this one. Now, a timer, usually you can look at it and tell how many seconds have passed or how many minutes have passed, but this timer is a little different. This timer is called an hourglass. And this hourglass has sand, or this appears to be salt in the bottom of it. And if you flip it over, this is actually what an hour would take for the sand in the bottom. If I flip it over, gravity is working on the sand and it's beginning to come through that tiny hole. It's going to take roughly an hour for all of this to drain into the bottom. And gravity is making that happen, okay? You can see it, it's beginning to fill, but it's going to take an hour before that fills up completely. Now, I will tell you this, it was about an hour since I last did this program. So I'm going to get that down. And I want to share something else about gravity. You know, while presenting this program, there's a couple of things I want you to be thinking about. And you've already heard a lot of the information that'll help you come up with a couple of answers. How can gravity change the position, direction, and the speed of an object? I think you guys pretty well know that now. And the other question is this: what force holds the planets in their orbit around the sun? You know, just taking the planet Earth and its relation to the sun and its relation to the moon, if you really think about it, we're in constant orbit, or we're revolving around the sun all the time. And that's what gives us our seasons, right? Well, not only does the planet Earth orbit around the sun, but the moon also orbits around the sun, and the moon also orbits around the planet Earth. Now I'm going to spin that around. And one of the reasons that we orbit the sun is much more massive than the planet Earth. Now, it's not really shown in this model, is it? It's humongous. And Sir Isaac Newton's thing was, the greater the mass of an object, the stronger the gravitational pull is. Now, I will tell you, somewhere around 28 times the gravitational pull of the Earth, that's how much the sun has. So it has a tremendous amount of gravitational pull, more so than what the planet Earth has. Now, we look at the mass of the planet Earth, it's a lot larger than the moon, isn't it? So our mass is greater than the moon. So we can hold the moon in orbit around our planet. And what should happen if, well, gravitation or gravity wasn't around? It would be really crazy, wouldn't it? And you know, it also has effect on animals around here too. You know, we know that birds can fly, but eventually they have to come down, right? Well, I forgot to put up an animal that I had used earlier this morning in a program, a bullfrog. Let me show you him. You heard Mr. Dominguez talk about push and pull. Well, this guy, he can really push off with these big feet. And of course, he can hop way up in the air, but you know what? He's got to come down. And the reason that he's got to come down is because of what? Gravity. Just think, on the moon, the gravitational pull is not as great as on the planet Earth. So do you think if he hopped up on the moon, do you think he would be able to hop higher or lower? Think about that. Well, I've run out of time, so I'm going to turn it back over to Dr. Gorman. And if any of you have any questions, I bet he can answer those for you.
Thank you, Mr. Monroe. And a student asked, what is gravity in simple terms? So I just did a quick little Google search with simple terms. Gravity is a force which tries to pull two objects towards each other. Anything which has mass also has a gravitational pull. The more massive an object is, the stronger the gravitational pull is. Gravity is what holds the planets in orbit around the sun and what keeps the moon in orbit around the Earth. Thank you again, Mr. Monroe. And now I am going to share my screen. During this virtual field trip, students observed how position and motion can be changed by pushing and pulling objects. Students also observed forces such as magnetism and gravity acting on objects. Ms. Ramirez told you how objects swing. Mr. Dominguez, push and pull. Ms. Schramm talked about magnetism, and Mr. Monroe covered gravity. Thank you for joining us. If you would, teachers, go to www.tiny.cc/3-5 feedback. Fill out a very short form and send it back to us. We would appreciate it.